Good morning, everybody, and welcome. We have the pleasure today to host Professor Giuseppe Bono from the University of Rome. He is an expert in stellar evolution, and in particular in stellar pulsation. He has been working for his entire career on stars and stellar population, and he is visiting us within the framework of the Severo Ochoa program. And he will be here for a month and a half until the end of November. And in case you're interested in talking to him during his visit, he is in the Severo Ochoa office above the cafeteria. So today's talk will be about metallicity gradients traced by Cepheids and RR Lyrae stars. So welcome, Giuseppe, to the ASE, and thank you for your talk.
Yeah. So thank you for this opportunity, for this invitation, and to be back in ESA for meeting all the new friends. Okay, so today I am going to talk about recent results that we have obtained using spectroscopic data for classical Cepheids and RR Lyrae. And I apologize whether I am mentioning only a limited number of collaborators. There is a color coding. We have young postdocs, PhD students, master students, and Clara is going to change the color pretty soon. So this is just a small number of the collaborators in these projects. A bit more in detail what I am going to discuss today. I would like to introduce you, in case you are not familiar with the metallicity gradients, and in particular the metallicity distribution of the galactic disk, thin disk. This is going to be a significant portion of the talk because I am going to talk about spectroscopic results based on significant sample of Cepheids, galactic Cepheids. I will introduce what we are doing concerning the metallicity gradient of the halo using the RR Lyrae, and in particular I will focus in the second part of my talk about what are the future plans, and in particular this opportunity to have a near-infrared spectrograph at TISO at entity, because this, in my opinion, is a great opportunity not only for the science that we are interested in, but also for other colleagues that might be interested in this observing facility. Okay, so I am always assuming that probably you are not very familiar with the kind of objects that we are talking about, even if they are classical objects. What I am going to do today is to talk about classical Cepheids, intermediate mass stars during central helium burning, and RR Lyrae stars that are in this region here, both of them in the so-called Cepheid instability strip. And this is, well, there are a number of similarities, but a significant fraction also of peculiarities between Cepheids and RR Lyrae. And I will mention later on what I am talking about. So let me introduce why Cepheids and RR Lyrae. You know, nowadays are becoming more and more popular, fortunately, these huge photometric and spectroscopic surveys in which you have tons of data. But quite often they are dealing with either red giants or even dwarfs, for which the possibility to estimate the distance and the age, individual distances and ages, is not easy at all. The advantage in using Cepheids and RR Lyrae, in particular the Cepheids, is the fact that we can provide individual distances with a precision better than 3% right now, even without Gaia, and we can provide individual ages. The problem is obviously that the Cepheids cover a limited age range. We are talking about something that is between 20, 30 millions and 300 millions. The RR Lyrae share some of these advantages concerning the distances, but do not share the same property concerning the age. In the case of the RR Lyrae, the only thing that we can say is that the progenitor is older than 10 gigayears. But we cannot discriminate between two RR Lyraes that have the same period because their property, their range in mass, the range in mass covered is too small compared with the range in mass covered by classical Cepheids. When I am saying demanding targets, I am polite. They are boring, okay? Because you need a lot of observing time in order to detect them, to estimate the mean magnitude, to estimate all the physical parameters. But you know, even if they are boring, there is a reward, and the reward is that once you have identified one of them, you can have a lot of more information. Okay, just to give you an idea, because in some cases a figure is significantly better than tons of words. This is a summary of the result obtained by Laura Inno concerning the Cepheids in the Large Magellanic Cloud in 6 bands moving from the VI from Ogle, JH and K coming from IRSF, that is a facility that Japanese have in South African observatory, plus W1, that is the Spitzer band. And what you can see there is that we are the spread in these plots, with the exception of W1, is an intrinsic spread. It is not dominated by photometric errors. Either there is a problem with the individual reddenings, but what you are observing there is essentially the intrinsic properties of these objects. Once you have calibrated the slope and you know the 0 point that can come from HST or Hipparcos or Gaia in the near future, you have the diagnostic to estimate the individual distances. So you have to account, we will see in a minute for the metallicity dependency, but this is the kind of approach that we use for all the Cepheids in our sample. Okay, I have briefly mentioned one of the two main issues. The main issue was about the distance. The other issue was about the fact that we are interested in using classical Cepheids and RR Lyrae as stellar tracers. But in order to be confident that what we are doing is rooted on numbers that have a meaningful error bar, we have to take advantage of the facilities that we have, in particular UVES at VLT, because these kind of instruments have high spectral resolution, is an 8-meter class telescope, and you can collect a spectra of this quality in which you can clearly identify a bunch of iron lines. This is specific for iron 1 and iron 2. But what is important is the numbers that are listed here. We are talking about hundreds of iron lines, iron 1, and tens of iron 2 lines. This was the work done by Katia Genovali in her PhD project, and at that time we were able, this is a few years ago, to have in this metallicity distribution across the galactic disk, this is the galactocentric distance, this is the metallicity, 1/3 of these objects were coming from proprietary data, plus Luke and Lambert, Luke and collaborators, Andrzejewski and collaborators, and you can see the kind of result we have been able to obtain, because all the other metallicity estimates available in the literature were rescaled, since we have an object in common, to the same metallicity scale. And what was emerging from the result obtained by Katia are, I will say, essentially 2 or 3 important ones. The first one is this increase in the spread when you are moving toward the outer disk. We are around 15 kiloparsecs, and there is clearly an increase in the spread in the metallicity in these objects. The second point is the fact that we have, this is a zoom of the same gradient, we have a clear evidence of a steepening of the gradient when we are approaching the inner edge of the galactic disk. Okay? So you have to think about that beyond this limit, you only have the galactic bulge. We will come back in a minute on this. And what is evident, in my opinion, is that even if we still have some spread, we have an increase by at least a factor of 2 in the iron abundance in the inner edge. Last but not least, the fact that at fixed galactocentric distance, you have to think about that all the times that you are estimating a metallicity gradient, you are folding the disk in 4. So this means that you are accounting for objects coming from different quadrants and at the same galactocentric distance. So what is emerging, and we have discussed this in detail, that this spread here has nothing to do with the errors. This is intrinsic, in the sense that in particular in these regions where you have this large spread at fixed galactocentric distance is due to the fact that the different regions of the spiral arms intrinsically have a large spread. And so this is what happens, shows up in the metallicity gradient with this increase in spread. But the two most important issues are the steepening of the gradient and the increase in the spread in the outer disk. Note that these kind of arguments, in particular the second one, is quite important for all the models that are dealing with the galaxy formation, and in particular the galactic disk evolution. Because there are models suggesting that this spread is somehow predicted, because at this distance, the disk of our galaxy should have a warp, and this warp is essentially caused, it has been only traced with gas. If the Cepheids are going to trace the same feature, this will be quite important to understand what happened in those regions. There is a paper by Mike Fist suggesting that this might also be the consequence of a merging of a galaxy that is entering in the galactic disk, in the galactic thin disk. Okay, but there is still a point. The point is that we are contributing with 1/3 of the objects, 2/3 come from different authors using similar data, because we are always talking about spectra with a spectral resolution that is higher than 35,000, but slightly different approaches, and even if we are confident that we can manage possible systematics, we are still dealing with different samples. So the next step was to try to improve what we have already done. I don't think that I am going to have time to discuss all these issues. I would like to focus in particular on the first two, because these are the most recent one and the most probably the most interesting as well. So what we have decided to do, I have to say that this was done essentially by Bastian, that was a master student, now he is in Göttingen, was to collect all the data available in the ESO archive. And you can see that we ended up with 1,000 spectra for 250 Cepheids, and with adding these spectra to what we have already done, we reached a sample that is our round sample is the 50% of the known Cepheids in the galaxy. And we contributed also with the 10% of new objects for which there was no metallicity estimate at all. And once again, the kind of approach that we used was to use UVES, ARPS, and FEROS. In this case, the brightness of the sample is decreasing when you move from FEROS 2.2, ARPS 3.6, UVES at VLT. And what is even more important, the fact that we have a bunch of cluster Cepheids to put together the metallicity scale of the open clusters with field stars, and we have calibrators, where calibrators for us means that we cover the entire, this was a mild definition, but we have Cepheids for which we have the coverage of the entire pulsation cycle. As soon as you put everything together, this is the distribution onto the galactic plane of the sample that we are dealing with, and the blue objects are objects in our sample. So what happens before we move on the results? Let me spend a few words about the approach that we use. Since the Cepheids and the RR Lyrae belong to the category of the boring stars, we need to know with some confidence what is the temperature, the gravity, and the microturbulence velocity at which the spectrum has been collected. And in order to do this, we are taking advantage of a huge amount of work made by Russian colleagues, in particular Kofiutuk and Gorlova, that provided more than 260 pairs that can be used. The method that is called line depth ratio. You can have an idea here of the pairs that can be used, or lines, neutron lines that are one close to the other, forming almost at the same optical depth, to estimate the effective temperature. And what is important is that a number of them are new. We are collaborating with them. A number of them are new, and in particular, they are covering a huge range in wavelength, and in particular, a significant range in effective temperature that is including all the temperatures of the Cepheids that we are dealing with. So this means that the most important parameter, that is the temperature of the object at which the spectrum has been collected, can be estimated using this approach. And just to show that we are not talking, in Italian we say we are not combing the dolls, this is essentially the temperature curve that has been estimated using these line depth ratios over the entire pulsation cycle for Zeta Geminorum. Note that not only the error bar, but the fact that we can trace the variation of the temperature along the rising branch. This is a very critical phase because is approaching the maximum compression, and what happens is that you have non-linearities in the atmosphere. With the old approach, based on a very limited number of line depth ratios, the error bars along the rising branch was significantly higher. So we are in the framework that we are assuming, there is a very solid internal consistency. Just to show you a few other objects with spectra collected with UVES, you can see that we are talking about a similar precision concerning the effective temperature. And now, the new estimate of the metallicity gradient. Well, there are a couple of points here that are relevant. The first one is this. Right now, we know 560, 540, something like that, Cepheids in our galaxy, and 500 are in this plot. So this means that we are talking about 90% of the known Cepheids before the Gaia era do have a metallicity estimate based on high-resolution spectroscopy. And what this gradient is suggesting is, once again, the gradient is of the order of minus 0.06 per dex per kiloparsec. As you can see, you can appreciate the spread here is reduced quite a bit, but the spread in the outermost regions is still present. This is not a real error bar. It's an error bar that is accounting for all possible combinations of all lines, not only those ones with an equivalent width smaller than 120 milliangstrom. So you have to keep in mind that this is only an upper limit. And these objects here are not truly classical Cepheids because they are significantly above the galactic plane. So what is important, I will say, in this context is the fact that we now have 0.05, sorry, I was quoting 0.6, but this is the gradient that we are talking about over the entire range of the distances for the classical Cepheids. And now, it is obvious that the most important issue now is to compare with what is known in the literature. The top panel is comparing all the metallicity gradient based on classical Cepheids. All these gradients have been artificially shifted in order to be identical to avoid problems with the 0 point at the solar circle. This is the reason why they are crossing all the same point. And you can see that within the errors there is a very good agreement concerning different authors concerning the Cepheids. And here, this is another important and fundamental issue about the chemical enrichment of the galactic disk, is that we are interested in estimating what is the effect of age. Effect of age is quite important because nowadays galactochemical evolution, the chemodynamical evolution models for the galaxy are suggesting that there is a strong impact in the chemical evolution due to radial migration and due to the fact that we have different regions of the galactic disk that can be affected by different enrichments. And what this plot is suggesting is that we do not have up to 3 gigayears within the errors. We do not have a clear, strong evidence of variation in the slope of the metallicity gradient, and it becomes more and more evident as soon as we are taking into account the metallicity gradient based on open clusters with an age older than 3 gigayears. Okay, so this is, in my opinion, already something useful to think about. We can go a bit more in detail about this issue. This is the comparison between Cepheids and OB associations, and you see that there is no difference. And this is once again the argument that I was mentioning before. Up to 3 gigayears, open clusters and classical Cepheids do not show any clear evidence of a variation. These variations start to become more evident, in particular the flattening of the metallicity gradient as soon as we move in the outer disk. Okay, I will probably jump these. I would like to discuss now a specific issue about the inner disk, the galactic center, and the galactic bar. There are models, probably the slide is coming in a minute, suggesting that the galactic bar, the bar, and the galactic center are fed by gas that is drifted from the inner disk into the galactic bar, from the bar into the galactic center. However, this is a sort of I would say, acid test to see how the plausibility of this scenario. And what is happening is that if this scenario is working hypothesis is correct, the metallicity in the inner disk, in the bar, and in the galactic center should be quite similar. The reason is very simple, because these are Cepheids, very young objects. These are red supergiants or blue supergiants, and the same applies for the galactic center. So this means that the age of the tracers that we are using is within 200 million years. The point is that we have evidence that the inner disk is significantly more metal-rich than the galactic center, and when compared with the inner disk. So this means that there is something else. The most plausible working hypothesis is that these regions, at least for the galactic center, we have a significant inflow of metal poor gas coming from outside that is diluting the regions in which we still have a very efficient star formation. Okay, since this is a long-term project and we are collaborating with Japanese colleagues from the Tokyo University, they are using this facility in South Africa, and they have discovered the new Cepheids in the third quadrant for which we know almost nothing, because they are heavily reddened, and the only possibility that we have to discover them is to use near-infrared detectors. So what we did is once we have, they have been discovered, we collected the low resolution spectra with ISAC, and the abundance analysis was performed by Miguel Orbanera and Norbert Prischbilla. And what we found for these objects is that they are once again located very close to the inner edge of the galactic disk, with the spread in the abundances where we have a clear evidence for some of these objects that are significantly more metal poor than predicted by the metallicity gradient. Let me say that in the meantime, colleagues, in particular Martin and collaborator, Andrzejewski and collaborators, have found also other 3 Cepheids that, according to the distances that they estimated, should also be in the inner disk. The error bar on the distance of these objects is quite large, because at least this one is only based on optical photometry, and the same applies for these other 2 objects. So I will say that it is not clear whether they are here or they are here, but there is a large error bar. And I will say that if we assume the most simple of working hypothesis, the extrapolation of the metallicity gradient of the Cepheids is also accounting for the position of these objects. Andrzejewski, I have to say that they claim that there is a sort of a flattening, but it is clear that the error bar on the distance and the fact that we do not have statistics does not allow us to reach firm conclusions about that. Once again, we are using all the new estimates for the metallicity gradient, metallicity estimates in the galactic center and the galactic bar, and you can see that the situation is not changing for nothing compared with what we have already found. Now, this is even more interesting because we are comparing now with the open clusters observed by the Gaia ISO survey. These clusters have an age that is ranging from several 100 million years to a few giga-years. And you can see that, once again, for the bulk of them, there is no clear significant difference compared with the slope of the galactic Cepheids. These are objects that have been observed by Reid and Schultes, but keep in mind that for these objects there is no possibility to discriminate their age. They are red giants. Who knows? They can be intermediate age, they can be old, they can be everything. Unfortunately for the red giants, we cannot say anything about the age. And finally, let me mention that there is a group of objects that have been identified by Cristina Cappini, suggesting that these are simultaneously metal-rich and alpha-enhanced, but they are not old. There are arguments based on the kinematics, but unfortunately, once again, we cannot reach the comparison between different tracers in this region is not easy at all. In any case, we are talking about 1 billion of years, nothing to do with ages that are significantly younger than 1 giga-year. Finally, let me stress that the mean metallicity here is still 0.1, which means that is, in any case, significantly more metal poor than what we have found. These are popular results because they are based on apogee, and they have observed a huge amount of red giants, and they are suggesting that there is a flattening in the metallicity gradient when you are approaching the innermost regions. I have to say that I am pretty sure that they are going to improve quite a bit the results. Right now we are facing this difference between warmer and cooler giants, but I will say that these are details. There is no doubt that they have a huge statistics, and in the near future they are going to be more and more precise. Note that Z is just the distance from the galactic plane. So as soon as you are moving outside, you will trace no more. You are not tracing anymore the populations in the galactic thin disk. And this is a similar plot in which there are different cuts concerning the sample that they have between in a surface gravity or in effective temperature. Okay, so now that we have discussed more or less the properties of these objects, let us move a little bit on the alpha elements, and I will show only two results that, in my opinion, are quite important. First is the fact that all the elements that we have investigated do show a gradient. In the past, there was some doubts concerning the possible occurrence of gradient of some of these alpha elements. Once you have accurate data, you are taking into account what is the variation in the different samples. We find that all of them, light metals and alpha gradient, all of them show the same, similar gradients. The other point that is quite interesting is the fact that we don't find any significant variation in the slope between alpha elements and irons. So this is, for those ones that are familiar with chemical evolution models, this means that the polluters, those ones that are producing iron, are also contributing quite a bit in the production of the alpha elements. Calcium is slightly different, but I am not going to discuss this. Finally, since this was one of the features that I was discussing at the very beginning, show the same gradient as a function of the logarithm of the period. So this means that objects that are here are, roughly speaking, 200, 250 million years, and objects that are here are around 20 million years. And you can see that all these stars, in particular when you have a very high precision on the individual measurements, you see that the gradient doesn't exist at all. Is just a mean value as a function of the period, suggesting that across the galactic disk, for the stars that we are tracing, they show similar enrichments, whatever is their distribution. Okay, I can discuss, well, this is a slide for those ones that are crazy about the anti-correlations in globular clusters. Field stars do not show that. And this is quite clear from, they show a correlation. Sodium and oxygen have a different history because, a different story because sodium is affected by non-LT effects. And the last one was about, yes, magnesium and calcium, because these two elements are tracing the hydrostatic and explosive yields, and you can see that it is pretty much constant, with exception of the metal-rich regime or super metal-rich regime, in which you start to see a difference when you are approaching this high metallicity regime. Obviously, you can play with a lot of other elements. We decided to play also with the neutron capture elements, and you can see that we have low, light, and heavy elements. We have also another element that is europium, and what we found is that within this sample that we are dealing with, the slope of these elements is not significantly different. And well, we can discuss the comparison with the giant and the dwarfs that have been observed by Reddy, and you can see that the comparison with the Cepheids are suggesting that there is no clear age effect between young objects and old objects. There is evidence of a peculiarity for yttrium for the galactic center. These are spectra collected in the near infrared by Livio Aurelia and collaborators with Giano, that is quite close from here. And well, the fact that we have positive gradients, this is over iron, this is a mistake. It's not negative, but positive, is the fact that the gradient of iron is significantly steeper than the S elements. I made a mistake in writing the word. What I would like to show once again is that probably with the S and R elements, we start to remove the degeneracy that we found for the alpha elements, because we start to have evidence of a positive gradient with period, and this is something that we are going to investigate a bit more in detail in the near future using other S elements that have not been involved in this process, in this analysis. And I would like to close the discussion about S and R elements showing this ratio in which we start to have evidence of a difference with objects coming from dwarf galaxies. These are the stars in Sagittarius observed by McWilliam, and also with galactic dwarfs. And you can see that these planes, that is lanthanum over europium versus lanthanum over iron, start to have a clear separation. And this separation becomes even more evident as soon as we are only using S elements, lanthanum and yttrium, because you can see that the bulk of these objects are covering a region that is not covered at all by the galactic stars. So this means that these S elements are quite good to understand the possible events of accretion due to the galaxies, so dwarf galaxies that have merged with our galaxy. Okay, I am not going to discuss probably in detail how much. 15 minutes. Okay, we are still in time. Okay, so I will only say one word about the comparison with the HB models. This is quite well-known result of the fact that the lanthanum over yttrium is correlated with the metallicity. An increase in the metallicity, an increase in the seeds, anti-correlated, decreases this ratio. And what we did was just to use the models provided by Cristallo and collaborators, and plotting on top of the results that we have obtained, of the measurements that we have performed. And you can see that there is a very good agreement, at least for the 0 point and the distribution, even if the spread is not explained by the current models for yields, the yields produced by HB stars. This is something new. We didn't publish yet, and this is a global overview of all the slopes in all the elements that have been measured with Cepheids. And what is interesting is that we have these trends in the SR elements, in the alpha and iron peak. These are the alpha. Calcium and titanium are also alpha, but we have also iron peak elements, and we have to understand why we do have these clear trends in groups of elements. Let me just say that current chemical evolution models are accounting for some of them, but not for others. These are affected by non-LTE effects. Sulfur is peculiar because we know it's an alpha element, but is not producing dust. These are elements that are, the observed slopes are significantly, so I have to go around, are significantly steeper than predicted by models. Okay, I like this slide because this is just, you know, we have always this problem that we are dealing with objects that are in the solar neighborhood, and these guys, Galactic and collaborators, succeeded in measuring a number of stars with KMOS at VLT in AGC 300 at 2 megaparsec, and they estimated the metallicity gradient. And you can see that even for these objects within the errors is not significantly different than the slope that we have obtained with Cepheids. But what is even more important, I do not have figures, but I would suggest you to go in taking a look at this paper. I don't know whether there are colleagues here involved in Khalifa survey. But it is really amazing the results that they have obtained, because there is a clear evidence that some of the galaxies in their sample show a decrease in the metallicity gradient when approaching the innermost regions of the galaxy. So what we are finding in our galaxy probably is not so peculiar once we put in context the Milky Way with similar spirals for which we have good data for estimating the metallicity gradient. So this is quite important. In my opinion, this is going to become more and more relevant in the near future. Let me move quickly on the RR Lyrae. The RR Lyrae is really amazing how poor is the knowledge that we have of their abundances, because this is a classical result obtained by Preston. I am pretty sure that Lucio remembers some of these papers by George Preston in the 60s, convincing the humanity that the RR Lyrae are very difficult, because along the rising branch you have the development of a shock, and this shock is changing quite a bit the temperature stratification, and this means that you are dealing with a huge amount of significant departure from local thermodynamic equilibrium. And so at the very end, this is just to tell you that we only have probably 60 RR Lyrae for which we have high resolution spectra available in the literature. 60 RR Lyrae for which we have metallicities based on high resolution spectroscopy. The other 3,600 that you can see plotted in this figure are only based on low resolution spectra. These are mainly coming from the Sloan plus Dumbies that was collecting data available in the literature, plus low resolution spectra collected by Drake is Catalina, Bivas, I don't remember the name of the survey, but in any case, interested in tracing stellar streams in the galactic halo. And this is the distribution that they have in the sky. If you put everything together, what happens is that you are getting something similar, in which you have here the galactocentric distance, you have the metallicity gradient projected onto the galactic plane, and this is only the Z component. And you can see that the gradient is essentially made by the distance on the galactic plane, because this is mainly contributing with this steepening of the metallicity gradient in the halo of the galaxy. Well, I am jumping to the conclusions because we do not have time. What is emerging is that if we account for the metallicity gradient that we found in the Milky Way, there is a huge difference with the metallicity gradient that has been found by Bata and collaborators using red giants, by Gilbert and collaborators using red giants, and this is with the stream, the tidal stream that has been removed. But you can see that in the range of galactocentric distances covered by the two gradients, there is almost 1 dex of difference. Something is quite different. Either the sample that they are using is not tracing the really, truly old population. Otherwise, we do have a problem in understanding the difference between these two halos. Now, a couple of issues that, in particular when the audience is made by young collaborators, there are a number of things that I didn't mention. The fact that for some of the Cepheids that we are talking about, we need to move in the near infrared because they are not visible at all, and the optical, they are too reddened. There are a number of arguments about the metallicity scale that is not homogeneous yet. We are working on that. There are a number of other issues connected with the calibration of the temperature, with the gravity, the surface gravity, and other points. And the list is even more, is longer, because what we have done right now is essentially equivalent widths, and obviously we have to move to spectrum synthesis. LTE, non-LTE, transition from 1D to 3D, There is a group of collaborators in Heidelberg that are dealing with this difference when you move from 1D non-LTE, 2D, LTE, 3D, non-LTE, all the possible mixes. And obviously, this is another important issue, and I'm going to discuss a bit more in detail. I only show one slide because one of the arguments that is used against the spread in the outer disk is the fact that in the outer disk we are essentially tracing type 2 Cepheids and not classical Cepheids. Fortunately, we do have spectral diagnostics that help us in identifying type 2 Cepheids because they show this Pissigny profile in the H-alpha, but this means that you need to cover the pulsation cycle, so it's not easy, and you have also the barium line and the helium line that can also be used for tracing the kinematics of the envelope, of the atmosphere of these objects. So we know how to do, but this requires a lot more observing time. And this is just to make more clear, this is a figure made by Miguel and Norbert, and I would like to draw your attention in particular on this plot here, because this plot here is essentially the difference in temperature, and you can see that there is a difference that is not, well, where is the temperature? This is 1,000 of degrees. You see between the non-LTE and the equivalent widths, there is essentially a 0-point difference. But the approach is different, and we are investigating. The difference is around 200 degrees, and we are investigating what to do. Finally, I would like to discuss something that we are working with colleagues here, in particular with the colleagues here at ESA. And this is something that is quite often in discussing the results that Gaia is going to provide us. Gaia is going to be a wonderful experiment because it is providing us distances for a lot of these tracers with a precision better than 1%. Okay? But the next step, once we have calibrated the period-luminosity relation, which means fixed the 0 point and fixing the slope, is to estimate the objects that we are interested in. Okay? And simple arguments concerning the propagation of the errors, here is the distance and the photometric error, is the fact that the bulk of these diagnostics do depend on metallicity. Okay? So this means that if we really would like to fully exploit the distance measurements provided by Gaia, we need to have photometry at level of precision on the mean magnitude better than 2%, and we need to know the metallicity with a precision better than 0.1, 0.2 dex. Why? Concerning the photometry is trivial. Gaia is providing the G-band. The G-band is useless. All the distances that we are going to provide for Cepheids and RR Lyrae are based either on optical or near-infrared photometry. So if there is a perfect period luminosity in the G-band, I need to collect data in the G-band for all the other objects that Gaia is not measuring. So, for example, if Giuseppina is crazy because she is looking for objects in 6822, it is clear that you cannot do that with Gaia. You need to have another photometric system. But if you are using a different photometric system, you have to transfer the relation that has been calibrated with the G-band in the V-band or in the K-band. There is no other alternative on this. Okay? The second point is that these calibrations also requires to know the metallicity with that level of precision, because the gamma coefficient that appears here, once we have to propagate the error, is of the order of 0.17 for the RR Lyrae and is of the order twice stronger for the Cepheids. So if, well, these are theoretical coefficients. Obviously, there is error. I am not saying that. But whatever is the error, we have to account for the propagation of the error in the metallicity in order to provide very accurate distances, very accurate diagnostic for the distances. And what we are trying to do is to follow two different paths. The first path is based on near-infrared spectroscopy, and we are collaborating with these Japanese colleagues that developed this instrument, wine red, and we are going to, we already succeeded in having nine nights at NTT the next February, moving this instrument, as you can see, there is a huge throughput because we are talking about 50% with a resolution that is around 30,000 and a very high resolution, which means around 80,000 that will allow us to measure all these kind of abundances that we are talking about. Just to give you an idea, these are the limited magnitude. This is a very efficient GRISM because it's a germanium GRISM. There is a patent on these. And I would like to draw your attention on these numbers here. Is covering Z, Y, and J. And these are the limited magnitude for a resolution of 14,000. And these around 15 for a resolution of 28,000 for 1 hour of exposure. So is really amazing, at least for those ones that are familiar with the near-infrared spectrograph. This is just a different way to show the same thing. The second part is the photometry. I have already talked about the problem that we have with the photometry, and this is a good number. I'm pretty sure that this is not very precise, but it's a good number to remember. And what we are trying to do is in collaboration, wow, the picture is not so nice, but I apologize for that. What we are trying to do with Matteo is to use your small telescopes here to collect time series data in the optical and in the near infrared for these objects that are relatively bright and for which the photometry is not available in the literature, and or if it is available, is for sure not homogeneous because it was collected during the 50s or the 60s. These are limited magnitudes that cannot be observed with a 4-meter telescope or an 8-meter telescope. You need to have small telescopes. And concerning the southern objects, we are going to use still use IRSF, for which we have 2 observing runs, one in November and the other one in December, 1 month with this telescope, 1.5 meters, that we are going to cover a significant fraction of the objects in the southern hemisphere. Okay, so let's say that we have, in the near future, we are going to have tons of data coming from optical and near-infrared spectrographs. But let me say that I am quite interested. This is the Galactic Center. This is really the mess concerning the dust, concerning everything. But what is important is that we have identified the green dots. The blue ones come from VVV. The green ones, sorry, the vice versa. The blue are from us, and the green comes from the VVV survey in identifying two dozen of Cepheids beyond the Galactic Center. Okay, this is the first time for which we have a clear identification of young objects beyond the Galactic Center. Keep in mind once again that this is essentially the bulge. Okay, you do not find young objects in these regions but the galactic bar. The young objects are located beyond the bulge, and these are going to provide us the first clear investigation of the chemical enrichment in the inner disk in a completely different environment compared with what we know on this side of the, in particular for the distance distributions, compared with what we know on this side. Obviously, I don't think that in the past there was any single period in which the variables are going to become or are going to become so popular, because Gaia and in particular LSST, I know that you are also involved in this project. It's amazing what it's going to do. Gaia is only going to scratch the tip of the iceberg. LSST going down to 27 or 25, this means that for the first time we will have the possibility to reach the outskirts of the galactic halo with solid tracers like the variables, but also with the dwarfs. Is something that we don't have right now. And the last one is only because I am addicted with E-ELT. Let me just mention a point that probably this is also very useful for the young collaborators. We are planning to have 6 instruments, 7, at E-ELT. On top you find the first light, E-ELT, CAM in the near infrared, integral field spectrograph harmony, mid-infrared that is called METIS. Maori is just the module for adaptive optics right now for Mikado. And then you have a high-resolution spectrograph and a multi-object spectrograph. The consortium is called Mosaic. All of them have a spectroscopic mode. All of them are going to work in the near infrared, for sure, because the adaptive optics are giving the best in the near infrared. So what we are doing right now with the near infrared spectrograph, high resolution spectrograph, is just to improve our knowledge of the fundamental physics lines, diagnostics for tracing temperature, gravity, microturbulence velocity. I didn't mention that right now we have the problem that in the near infrared it has not been identified any single R lines for R elements. We have ideas on how to do that, but right now they have not been identified. All this work is going to become fundamental as soon as we are going to use these new facilities that will become available in the near future. Okay, and I have already mentioned the discussion, and thank you for your attention.
Thanks, Professor Bono, for the interesting talks. We have a few minutes for questions.
Yeah, I have 3 short questions, let's say. So in relation to the difference in metallicity between the halo of the Milky Way and the halo of M31, M31 is a quite rich halo, which probably have like 10 times more mass than the Milky Way halo. So I was wondering whether this could be the reason why the metallicity is higher. I mean, probably because the progenitor, the dwarf that has been involved in the formation of the halo of M31s are larger or something like that.
May I answer one by one?
Sure.
Yeah. Okay. This is a good argument, but the point is the following. If you trust on these simulations, they are suggesting that we are dealing with a double halo, an inner halo and an outer halo. There are also empirical evidence that this is the case, in which the inner halo is essentially formed in situ and the outer halo was accreted. The problem that we have in analyzing both the Milky Way and the M31 is that we don't see any clear variation in the metallicity gradient. Even more important, within the errors, the spread around the metallicity gradient is quite small. This is moving in a direction in which we are also working. Probably the kind of merging that these galaxies experience is not made by hundreds of small galaxies, but a few giant dwarf galaxies. It's an oxymoron. But I am talking about galaxies like the Magellanic Clouds, like the Sagittarius. These can probably account for what we are observing right now. The difference between the halo and the M31 and the Milky Way, you are right, there is a huge difference between the two. We have a clear evidence of this giant stream that has not been, well, if you think about Sagittarius, Sagittarius is a giant string. But we removed the Sagittarius from our gradient, and you have and you can see that even if you are removing the tiled debris from the M31 halo, the slope of the gradient is not changing significantly. I am saying that we need more data before we can reach significant conclusions. The mass, for sure, is something that is somehow explaining the difference between the two, but is, in my opinion, is not totally explaining.
Yeah, my second question is connected to the decrease in metallicity in the bulge region compared to the increase that you are seeing in the inner disk. I was wondering whether you have a limitation, observational limitation, in the sense that when you go to and explore the bulge, you are exploring the bulge, this is my question, above the plane of the disk significantly. And this could be partly the reason why the metallicity is decreasing, because for instance, you were showing that at the distance of the sun, also the metallicity of our disk is decreasing at a higher altitude over the disk. So I was wondering whether this is
okay, I can answer. I guess that you are talking about this one.
Yes.
Yeah. So the point is that in the bulge, there are no Cepheids. The only ones that you can find are either along the bar, and what you can see here is just the near end of the bar, or in the galactic center. The rest of the populations in the bulge are essentially intermediate age or old. So the advantage, and unfortunately we didn't yet reach this point, is that we have identified the Cepheids in the galactic center. At that point, we are using exactly the same tracer to show whether these objects have or do not have. But concerning the bulge, I think that there is no room to what we know right now, the fact that there are no young populations there.
I know, but I mean, my question is, what about the altitude over the disk plane when you are studying the bulge? Are you exploring the high part of the bulge, or you are exploring the very central part of the bulge?
But are you talking about the Cepheids or the RR Lyrae? Because in the RR Lyrae we removed completely everything that is inside the 5 kiloparsecs.
The Cepheids, I'm talking about this.
About this, I think that there is no. Wait a minute. For the Cepheids that are in the outer disk, beyond the galactic center, because for those ones that are on this side, we do not have a problem at all concerning the identification of the Cepheids if they are there. I'm not finding there. So probably I am missing your question. Because if we are talking about the objects that are beyond the galactic bulge, you are, no.
Let's, I mean, you show evidence that when you move above this plane,
yeah.
Even at the location of the sun, at the distance at 8 kiloparsec from the center, you show that above this plane, as soon as you move out, the metallicity is decreasing. Okay?
Ah, okay.
So then my question is, when you study the bulge, you are probably limited by the position about the disk plane of the bulge, because it's dominated by the dust or something like that.
Okay.
So I was wondering whether the metallicity that you are inferring from the bulge is the bulge, but in the upper regions, I mean, in the high altitude.
Okay, in the case of the Cepheids, we can be quite sure that all the samples that we are using are confined within 500 parsecs of the galactic disk. So this is our current, I will say, Occam razor to split the samples. So whatever is above this limit is not, might not be a classical Cepheid. Okay,
my final question is more. I mean, it's when you're using the Cepheids, you are saying that you are exploring somehow the metallicity right now. I mean, because you have a very homogeneous and young population. So my question is, can we say something about the initial mass function using the Cepheids, the initial mass functions today?
Well, this is a good point. We didn't, but in order to do that, for some regions probably we can, but not entirely. And the problem is that we are not complete, because the galactic plane is obscuring a significant fraction. So I would say that in the solar neighborhood, we can do that. And this is something that we have now the data for analyzing the IMF. I fully agree with you. The thing that I can already anticipate is the fact that as soon as you are moving into the metal pure regime, which means in the outer disk, you are missing the long period ones. So this is telling us that is somehow connected, but not entirely, that the metal pure objects do not develop a blue loop that is crossing the instability strip. So the point is that you need to know, in order to constrain the IMF, not only the Cepheids, but also the objects that are bluer or redder, in order to have a solid constraint on the IMF. Because there are also evolutionary reasons why the Cepheids might not be produced. And this is a deficiency in developing the blue loop.
Yeah, I have two questions. One, in fact, related to Nacho's question about because you plotted regarding the abundance ratios.
Yes.
But you plotted only in the galactocentric distance.
Mm-hmm.
And you don't see any.
You're right.
Well, maybe a little bit on
calcium.
Yeah, but how about did you plot on Z?
Bravo.
That's the point.
Bravo.
Because we do find a significant
azimuthal effect
for iron in bulges of external galaxies. No, that's one question. The second question is regarding this steepening of the metallicity in the very central, let's say, well, not the central, but I mean
approaching the inner
approaching
disk.
the center. No, you got two different ways to determine the metallicity. So you talked quite a lot about the problems with the offsets in metallicity, or because the methodological approaches you're following or the, and then, but this is a really sharp steepening. Is it so well calibrated with the in a metallicity regime that it's let's say above plus 0.2 or plus 0.3 or something like that? This is key, because it's where you.
Yeah, you are absolutely right. Okay, so let me answer to the first one. I didn't show with the 5 Cepheids that we have in the third quadrant. We are repeating this experiment about the azimuthal effect, and within the current sample, we don't find it. So whatever is the direction that you are moving around, we don't find any clear evidence of an azimuthal effect. I know that this has been found by different authors, including Ben Davis, including measurements of H2 regions in the outer disk. But using the Cepheids, we don't find this azimuthal effect. We are still investigating, but right now we do not have a clear evidence. Yeah, on the vertical component. The second question is extremely interesting, because it is moving in the direction that I was mentioning before. And you are right, whenever you are at 0.4, all the a significant fraction of the lines that we have used for the other Cepheids are saturated. So it was really a tough job, because only spectra with a signal-to-noise ratio above 300 could be used to identify a good number of iron 1 lines and iron 2 lines that could allow us to be in the linear regime of the curve of growth. And so I will say you are absolutely right, and it was really difficult to be sure that we could apply the same approach in measuring the metallicity in this super metal-rich regime and in the metal pure regime. But we analyzed it. It was discussed the fact that the line list has been changed by probably more than 50%, the lines that we are adopting to remain in the linear regime.
I will say to finish here, but if you want to continue to talk with Professor Bono, you can go to the cafeteria at the scientific coffee. Thank you.
Very welcome.
Thank you.